Now, after we get the SPT N blow, then what we can do? This SPT blow is very important because this parameter can correlate to the 100 shears, right? CU of QU. So this is the bearing capacity of soil. Yeah. So this is if you have very hard. So this is very soft. So this is for N less than 2 is less than 25 kPa. For SPT less than 2, the CU is about 10 kPa. So this half of that, about half of that CU and bearing capacity 100. So based on the SPTN value as well, you can get the another correlation, which is the Young modulus E. So based on N value, so you can convert that to get the information of Young modulus. It is especially based on different type of soil. They have different empirical formula. This is empirical formula for different type of soil. Okay, to get the Young modulus. Another is a rock core. Based on that SI, we can get rock core. This is example of rock core. You can see this one rock. You can see this rock. This you can see the fractured. This fractured, and also you can see this fractured. So we need it here, and also you can see this fractured. Based on this rock core, you can check the how fractured this rock. This rock more fractured. This more fractured than this. This one more quite okay. Compared to this one also okay. See quite far the fractured spacing. So this is what is sample of rock you get. Okay, look on this video how they take out the rock sample from the core barrel. This is our core barrel. Okay, core barrel.
Pressure,
Pressure here. And after the calling, they want give the sample that out from the core barrel. This core box. You can see. Okay, you see how the length from here to the whole core barrel is 1.5 meter. So just imagine only 1/3 of that sample, not fully full with the sample. So we get here based on that sample, only 1/3 of sample recovery. So we can get total core recovery. Based on that, also we can calculate the RQD, rock quality designation. Okay, based on that sample, we can see that we can calculate the rock total core recovery. How many how length sample that we can get from this core, and then the fractured system we can calculate based on the rock quality designation RQD or solid core recovery SCR. Okay, definition of RQD. RQD is we calculate the fractures that or any core that length that more than 10 centimeter. We are count it as a core length. If less than that, we are exclude in the calculation. For example, this one less than 10 centimeter, we exclude from the calculation. Is for RQD. But for solid core recovery, any fractured in any sample not in the fully diameter, we not exclude for the calculation. So this is for solid core recovery. For total core recovery, we have to, for example, this we have to measure the length of this core, then divide by the total core length. Total core length is 1.5 meters. So let's see, we can get here 0.3 meter. So 0.3 divided by 1.5 times 100. So we can get DR, total core recovery in percent. So this is how we evaluate the rocks, or presenting, reporting the rocks quality. So normally in rocks, we are core up to 6 meter for granite to confirm it's not boulders, or 12 meter for limestone area to prevent any cavities or pinnacle or sinkhole. So meaning that scoring is length is depend on the formations. Also rock, based on that rock core, we can do this uniaxial compression test, triaxial compression test, point load test, mid hammer test, and then we can do this calculation for rock quality dimension, total core recovery, solid core recovery, fraction index. So this is parameter is important in rocks classification. Sometimes they use for rock mass classification or soil rock classification. So this how we measure total core recovery. As I said, core recovered core recover more than 10 centimeter. Sorry, this total core recovered divided by length of core times 100. This is core recovered sample. And then solid core recovery is solid core pieces in full diameter. If we have full meter like this, so it's counted. If we have this sample but break here or break somewhere here, so we not counted. And divided by length of core is 1.5 times 100%. Last, we have the rock quality designation solid core piece that more than 10 centimeter, or 10 centimeter or 100 mm, which is we have piece of like this that length more than 10 centimeter, we count it. Any less than 10 centimeter, we exclude in this calculation. And then the fracture index is number of fracture divided by length of core. Okay. This is an example of question in our test. So meaning that here you can try at home. So this is based on 1 meter core length. So they ask you to calculate the rock RQD, solid core recovery, and total core recovery. So based on that, you can calculate the for RQD any core that more than 10 centimeter, 10 or 100 mm. This is more than 100 mm. So this is more than 100 mm. Only this and this and this. Then you plus, and then you have to divide by 100, 1.5 millimeter, 1,500 millimeter, and time 100, and then you get this value. For solid core recovery, so this solid, this not solid, yeah, this not solid, this not solid, exclude this one, others you can count it, even not less, even more than less than 100 mm, then you can get the solid core recovery. For total core recovery, you count all the samples and divide by the total core length times hundreds. That's how you evaluate the rock core. This is an example how you describe the rock quality based on rock quality designations. So if you have get less than 25, it's very poor. 25 between 20 and 50 poor. Moderate 50 to 75. If very good is more than 90%. So in terms of measurement of RQD, this is we call that direct method. We have another technique, we call that indirect technique to measure the RQD. This one is we will discuss on when we are in the rock mass classification, indirect technique. Sometimes we not do this borehole, but we can, based on the outcrop or rock exposed, we can measure RQD. We call the technique, we call it indirect technique, based on window technique. Sometimes we can use the seismic to estimate the RQD seismic. So then now we know that this is the limitation of the seismic. The seismic is limitation is the data is only at the drilling point. So we have, let's say you have a 30-kilometer road, so that point only represent at this specific location. So you have to do the interpolation between the borehole. So how close that borehole that you need to do. So if you have very close spacing, and then your cost is really jump. But if too far, your borehole is too far, you have uncertainties in between this location. So that's the interpolation between the borehole involves some degree of uncertainties. Let's say you have every 1 kilometer you have a borehole. Let's say borehole 1, borehole 2, every 1 kilometer, then in between, then you have to do the interpolation between this borehole, because you want to get the profile along the alignments, road alignment. So where is the rock layer? Let's say you get rock here, so you have to do the interpolation to get the rock level or boundary between the soil and rock, or you can get the soil profile. This is low, weak soil, hard soil, rocks, for example, like that. So this involve a certain of degree of certainty, because the only which are on the drilling point only. So sometimes we have error in do this borehole study. So to overcome this problem, so we have to do another technique, which is we call that geophysical technique. That geophysical technique is introduced, have advanced technique in all industry. Now we use in the constructions.